And okay, our speaker today will be Kate Scholberg. She is professor of physics at Duke University. Kate is an expert in experimental neutrino physics, and she has worked at many different neutrino experiments. For instance, she is a member of the Superkamikande and T2K neutrino oscillation experiments in Japan. And she is also a member of the Future Dune experiment, where she is one of the conveners of the Supernova burst and low energy physics working group. Kate also coordinates SNEWS, the Supernova early warning system. That this is an experiment and collaboration that provides sensitivity to galactic supernova and provide the astronomical community with a prompt alert of a galactic or collapsed supernova. But today, Kate will talk us about a different subject. So she was the spokesperson of the Coherent experiment, and today she will tell us about the first detection of the coherent elastic neutrino-nucleus scattering by the Coherent. Thank you.
Okay, thanks very much. It's a great pleasure to be here, and thank you everybody for managing to swim here. Here's what I'm going to tell you about. I'm going to talk about coherent elastic neutrino-nucleus scattering and talk about the physics motivations for measuring it and how one goes about making that measurement. I'm then going to talk about the coherent experiment at the Stellation neutron source and about the first light measurement with cesium iodide and its interpretation, and then talk a little bit about future prospects for coherent. Okay, so coherent elastic neutrino-nucleus scattering, or SEVNs, this is a process in which a neutrino hits a nucleus by exchange of a Z boson. It's a neutral current process, and the nucleus recoils as a whole. This is a coherent process for neutrino energies for medium-sized nuclei up to about 50 MeV. And, oops, what happened? It's weird. Okay, there we go. Okay, I think I'm hitting this thing on top of it. Sorry about that. Okay, I think I'm calibrated now. So what I mean by that is that the process happens such that the nucleon wave functions in the target nucleus are largely in phase with each other, which is a higher probability at low momentum transfer. And the quantitative criterion for that is that the momentum transfer times the size of the nucleus should be small. And if this condition holds, then this property should hold as well, which is a fundamental property of coherence, is that the total cross-section for the process goes as the single constituent cross-section times the square of the number of constituents. So that's the hallmark of a coherent process. Just to make this is really for high-energy neutrino people who might be in the audience. This is not coherent pion production. This is an elastic process where the nucleus retains its nature before and after, and there are no additional particles produced. Coherent pion production, you actually have additional particles in the final state. Mass energy turns into pions. And this is an interesting process in its own right that high-energy oscillation people study, but it is not what I'm talking about. I was actually once invited for a talk, and the people who invited me thought I was going to talk about this, and they were very disappointed. I'm actually talking about elastic processes. And here's just a little aside here on nomenclature. If you look in the literature on this process, you'll see many different acronyms: CNS, CNNS, CENNS. I like to include the E for elastic for just the reason on the previous slide is I want to be clear it's an elastic process or it gets confused. I've been chastised by nuclear physicists for using NN because to them that means nucleon-nucleon. You can put a little Greek letter there, which I'm okay with, but it's always annoying if you have to constantly change your font. And so I like to call this SEVNs, where the V is a nu, and it's pronounced like seven, so please spread this meat. This is I'm going to talk about SEVNs. Now this process was first proposed by Dan Friedman, a theorist, about 44 years ago, and he called his suggestion an act of hubris because of the grave experimental difficulties in actually detecting the process. And so what I'm going to talk about is how we've actually overcome these difficulties. Now the cross-section for this process is actually, by neutrino standards, really large, and that's due to the coherence of the interaction. This is the cross-section here for the process, for the example of cesium and iodine as a function of neutrino energy. The cross-section here goes according to the square of the weak charge the nucleus, and this is the number of neutrons, this is the number of protons. Sine squared theta W is a fundamental weak parameter, and it's about a quarter. And 4 times that then is about 1, and so this prefactor is about 0. And so this process is dominated by the neutron content of the nucleus, and it goes as the square of it. So here are some other popular neutrino interactions for experiments. This is elastic scattering on electrons for cesium per target atom and cesium iodide, which is a small cross-section. This is inverse beta decay, that's electron antineutrinos on protons, which is a famous interaction in neutrino physics used for many experiments. This is regular old charge current interactions on iodine of electron neutrinos. And then the process I'm talking about here, sevens, is orders of magnitude larger than that. So by neutrino standards, it's a process that should be happening all the time. And so you might ask, well, why is it such a difficult thing to do? If it's a high rate process, why is it hard to observe? And the answer is kinematics. Even though the cross-section is large, it's like hitting a bowling ball with a ping pong ball. That's easy to do, but it's hard to get the bowling ball moving very fast. And so what you have is a situation where the recoil of the nucleus is really very small. And so this is an example. This is for a 30 MeV neutrino on a target of a medium-sized nucleus, germanium. This is the differential cross-section. T is the recoil energy that you get. This is kinematic factor here. The maximum energy is when you have, the maximum recoil energy is about 2 times the electron energy squared over the mass, and if you plug in the numbers for germanium, that's about 25 keV. And this is very tiny by neutrino detection standards. If you take a detector like Super K, the threshold for seeing anything at all is about 4 or 5 MeV. And so this kind of thing is completely invisible. So these are very hard to observe experimentally. The only way you can actually see it is to look for that little tiny bit of recoil energy that couples into something that you can actually digitize and see. And that's challenging. So you get a recoil that will deposit energy in some way that can couple into some channel. But the thing that has happened since Dan Friedman's time is that there's been a huge amount of detector development that is focused exactly on this problem, on actually trying to gather this little tiny bit of deposited energy and turn that into something observable. That's basically what a WIMP, a weakly interacting massive particle, does, is it will make a little recoil, it'll bump into some nucleus, and you get a little tiny bit of energy. And currently we have actually quite a bit of detector technology that is sensitive to a few keV, up to a few tens of keV recoils. This is also, neutrino interactions of this sevens interactions also make up what is known as the neutrino floor for dark matter detection. So this is the kind of plot that if you're a dark matter experimentalist, you put this on your t-shirt. This is the parameter space, this is a cross-section for WIMP interaction, this is the mass of the WIMP. These are the kind of curves that different experiments can, ideally they would like to put an observation on this plot, but typically they will exclude regions if they see no signal. And this line here represents the dark matter parameters at which you start to run into sevens background from natural neutrino sources. And so if you're around, if the dark matter parameters are around here, you will actually, if you have a detector that's sensitive to that, it will actually see a significant number of sevens interactions from solar neutrinos from the sun. Here it's relic supernova neutrinos, and here is atmospheric neutrinos. And so this is the famous neutrino floor for dark matter detection. And so it's interesting to measure this sevens signal, because there in fact may be non-standard contributions to it, in order to understand the nature of the background for dark matter detection. Okay, so here's the cross-section in the standard model. It's very straightforward. It's a simple and cleanly predicted cross-section. These are the standard model weak parameters, GV and VA, the vector and axial contributions. For most nuclei, for most targets that we're talking about, the vector contribution is very much dominant. It depends here on the protons and neutrons, where this one is the neutron contribution is larger. There is an axial contribution that depends on the spin. But because the unpaired nucleons in most nuclei are very small compared to the total number of nucleons, this tends to be a very small contribution. So it's really a vector interaction we're talking about. And if you have a spin zero nucleus, it's entirely vector. There's also this factor in here this is a form factor, a nuclear form factor, which it's the Fourier transform of the nucleon space distribution. And this gives you a suppression at high momentum transfer. It actually quantifies the coherence of the interaction. At high momentum transfer, you start to scatter off the constituents of the nucleus instead of the nucleon instead of constituents of the nucleus instead of the nucleus itself. And so here's an example. This is plotting the form factor as a function of momentum transfer up to 100 MeV. The bigger and fatter the nucleus, this is xenon and this is neon, the bigger and fatter the nucleus, the more suppression you get of large Q, the more the structure matters. So what we would like to do, if we're trying to measure sevens, is to measure the dependence on the square of the number of neutrons in the nucleus, basically this coherent property of it. And so here now, this is cross-section. This is actually averaged over a flux from pi to k at rest, which I'll tell you more about in a bit. This is the cross-section as a function of neutron number. This black line here is if you treat the nucleus as a point particle, so ignoring the form factor, you expect a fairly clean n squared dependence. This green here is if you include the effects of the form factor, which is quite well known from nuclear physics. It's not perfectly known, but this width of this green band represents the uncertainty on that form factor, so it's a small uncertainty. And these points here are the targets, the particular nuclear targets that I'm going to talk about, and as I'll show you, we have one measurement made and we have more to go. And I just want to point out at this point here that a deviation from this n-squared prediction could indicate some kind of new physics, since this is a standard model prediction. Okay, why should we measure this? I think I've actually already given you a couple of motivations. So this is a slide from Alicia Lisi that I really like, that he showed at the Neutrino conference in Heidelberg last summer. It's many possible reasons. He calls them small but multicolored. And here are some of the reasons for measuring it. So one I already mentioned is that it's a dark matter direct detection background. So if you want to understand the background for dark matter, it's a good thing to measure this. A second one I already said something about. It's a very clean cross-section in the standard model. If you interpret a result in terms of the standard model, you are making a measurement of standard model parameters. But maybe more interestingly, it's a probe of beyond the standard model physics in that you can get deviations from expectation by new interactions of neutrinos and other non-standard model physics like neutrino magnetic moments. It's also a tool for looking for oscillations into neutrinos that have no weak interactions at all. There are other reasons. You can actually use this process for astrophysics. I'll say a little bit about supernova neutrinos. And it's actually important in supernovae themselves. And you can do some nuclear physics as well if you can really measure it precisely that you are probing the nuclear structure. If you can get better than a few percent, you can actually start to understand properties of the nucleus. And then finally, it's such a large cross-section that there have been proposals to even use this for practical purposes, for example, to monitor the neutrinos from a nuclear reactor. Okay, let me zoom in on a couple of these. I'm not going to go through all of them, but I'll say a little bit more about some of them. So first of all, searching for beyond the standard model physics. If you have a non-standard interaction of a neutrino with a quark, it in fact is quite poorly constrained as yet. And these are the so-called NSIs. There's actually been a lot of work, theoretical and experimental work on that in the last decade or so. This is a parameterization that you see frequently in the literature. It's not the only one. It's not really model independent. It's kind of a simple model. But here the idea is that you write down a Lagrangian and you have extra interactions that are parameterized by these epsilons, which depend on the flavor and also can describe a flavor changing interaction as well. These quantities, if they're of the order unity, it describes an interaction which has a coupling which is about the order of magnitude of the standard model. And in fact, up until now, there's actually fairly poor constraints of some of these interactions. Nobody's ever really probed these recently. And so the signature you get, the experimental signature that turns into, are an excess or deficit of the sevens rate compared to the standard model expectation. And this is just one example. This is a parameter space where you assume all of the epsilons are 0, except for one that describes an interaction of electron neutrinos with up quarks and electron neutrinos with down quarks. And so basically epsilon, EE, vector, there could be axial ones as well, and EE on up quarks here. And so here's what you would actually get. This is the color represents the ratio of the rate of sevens you would get with respect to the standard model in example of cesium iodide. If you have, you can have negative or positive epsilons, and so you can actually have accidental cancellations such that you would actually happen to get the standard model rate. So if you measure the standard model rate of the interaction, you can't constrain the parameters. And so that corresponds to these pale lines here. But if the parameters live here, then you would get a lower rate than expected. If the parameters live out on these wings here, you would get a higher rate of sevens than expected. And so that's the idea, is you compare your sevens rate to what your expectation to constrain the possible parameters. And it turns out here, this is another relatively recent work by Pilar Coloma and Tom Stretz and other collaborators with subsequent papers. The idea here is that you can actually mess up mass hierarchy determinations in long baseline experiments by having extra interactions that fake a particular oscillation spectrum. And so here the idea is that if you have a normal ordering and no NSI, you can actually get the same answer by having an inverted ordering and some NSI. So this is actually a fundamental ambiguity. And so what that means is that if we can constrain some of these parameters using sevens experiments, we can actually remove some of these ambiguities. And so this is actually very interesting. And furthermore, for Dune, we could actually even potentially confirm an NSI signature. Here's another example, is sterile neutrino oscillations. And so if you have oscillation into a sterile neutrino, that neutrino will not interact at all by any kind of weak interaction, and so you would get a disappearance of the sevens rate as a function of baseline and energy. Sevens is neutral current, doesn't care about the flavor, so disappearance is really a true disappearance. Furthermore, the recoil spectrum has information about the neutrino energy in it, and so you can get information on the dependence on energy at some level. And if you have multiple detectors, you can cancel systematics. This is an example here of a relatively recent paper looking at the sensitivity. If you can't read that, this is the sterile mixing and mass difference squared for different detector configurations. This assumed 100 kilograms of germanium, which would be pretty hard, but in fact you can get large amounts of other materials. One more here, neutrino, actually I have a couple more. Neutrino magnetic moment. Here in the standard model, you expect the neutrino magnetic moment to be really, really tiny, but there are, beyond the standard model, physics that could give you something anomalously large. And the signature of a neutrino magnetic moment is that you would have an excess of recoils at low recoil energy. And so this is an example here. This is for germanium. This is the standard model expectation of your differential recoil spectrum as a function of recoil energy for approximately 30 MeV neutrinos. And here is what you would get if you have a neutrino magnetic moment of greater than this would be greater than the standard model expectation, but this is the signature you would expect. And in fact, there's been various explorations of that in the literature. And then it's also, in the context of the standard model, it's a method for measuring the weak mixing angle. This is the effective weak mixing angle as a function of momentum transfer over many orders of magnitude. And in fact, there are some neutrino anomalies still out there. What you can do by measuring the rate is you can infer what the mixing angle is if you make the assumption that it's a standard model process, and it would be at this value of Q, approximately. Here are the experiments that I'm going to be telling you about. And so it's a new way of measuring of the weak mixing angle. Then, as I mentioned before, if you actually have enough momentum transfer, you are actually rattling the nucleus a little bit, and you can learn something about the distribution of the nucleons inside the nucleus by measuring the form factor, which gives you an observable in the recoil energy distribution. So here, as a function of Q, you actually get you'll get a different recoil energy distribution. And there have been actually various papers in the literature showing how this is actually something, if you can get to the few percent level, you can make really meaningful measurements of the nuclear physics going on. Now, I also want to make a mention, this is one of my favorite things, is neutrinos from core collapse supernovae. If you have a star near the end of its life collapsing, the binding energy of the resulting compact remnant, which can be a neutron star or a black hole, goes almost entirely into neutrinos of all flavors with tens of MeV energy. That's basically because it can escape via neutrinos. And it's mostly in the form of neutrinos and antineutrinos of all flavors over about 10 seconds. And so here's an example of a particular model on a time scale of about 10 seconds. Basically all the flavors are present, especially in the later times. And what you would get in a dark matter detector is 7's recoils. You get a bright burst of 7's recoils all within about 10 seconds showing up in a dark matter detector. And so here's an example. This counts over a threshold, and here this is MeV, so this corresponds to about a 10 keV threshold here. These are different materials that are used for dark matter detection, so argon, germanium, and xenon. And so here what you can see is that per ton of material, and dark matter detectors are now getting up to ton scale, you get some tens of events, maybe 10-ish events or so above a recoil threshold, which is actually, these are the kind of reasonable thresholds you can expect for these experiments. And this is important because it's sensitive to the entire flux. Supernova neutrinos, mostly like June or Super K, are sensitive only to electron neutrinos or antineutrinos respectively. This kind of interaction sees the entire flux of a supernova. And here's an example. This is a recent paper exploring specifically xenon detectors used for dark matter. And the scales of these here are currently in the few ton scale, but in the future there are plans for detectors going up to the several tens of ton scale, and that would actually give fairly significant statistics for seeing the entire flux of a supernova burst in a galaxy. And this here shows a detection significance as a function of supernova distance. This is the other side of the galaxy, and so it would be quite significant detections. And I just want to make the point here, this dip here in the neutrino floor for diffuse background supernova neutrinos is about 9 or 10 orders of magnitude. The flux here creating this background is 9 or 10 orders of magnitude smaller than the flux you expect instantaneously during a supernova burst. So you can kind of think of the supernovas, it's like the neutrino floor coming up to hit you in the face. Okay, so now let me talk about detection. So how do you detect 7s? You need a neutrino source and you need a detector. So let me talk about the flux. So what you need for your source is, first of all, you need lots of neutrinos. That's always true if you want to do neutrino physics. Neutrinos are notoriously weakly interacting, so you need lots of neutrinos and or a large detector. You want to have a spectrum which is well understood. And that's important if you want to test the standard model, because you want to test your recoil spectrum against the expectation, which depends on the neutrino spectrum, so you need to know your neutrino spectrum well. You want to have lots of flavors. You would actually like all of the flavors and to know what your flavors are, since new physics may have a flavor dependence. You want to have a pulsed source, if possible, and this is very important for experimental work, and this is used frequently for long baseline neutrinos, for example, or actually any kind of accelerator neutrinos. You want all your neutrinos to come in very sharp pulses, because that allows you to reject background outside of the pulse, and you can also characterize your background outside of the pulse so that you can subtract it. So this is actually practically a very important benefit, if possible, to have a sharply pulsed source. And then there's practical things. You need to be able to get close, you need access and control, and so on. Okay, so here are neutrino sources that could, in principle, be used for 7s. So you want to have a, and some of them have different properties. So we have reactor neutrinos, which are low energy sources. They go up to several MeV, and you can get very high fluxes, but they are not pulsed typically. They are continuous wave sources, and so you need good background rejection. Then there's the one I'm going to tell you a lot more about, which is pions from decay at rest. stopped pions. These are higher energy. You can have them in a pulsed beam. There are potentially particular backgrounds to worry about. Then there's some other ones, and these are all kind of, at the moment, not really technically feasible yet, although there's development towards them. There are radioactive sources. These are very low energy. These typically less than 1 MeV or so, and that means the recoils are even lower energy, so that's technically challenging. You can have beam-induced radioactive sources, and these are also potentially interesting, but are still under development. And then there's beta beams. You can make a storage ring of radioactive nuclei and actually boost the products at will. And this is not pulsed either, but is tunable in energy. But this also does not exist yet. In fact, I'm not sure there's really active development right now. But I want to zoom in on these two, which are existing sources. So neutrinos from nuclear reactors are in the few MeV range. So typically 3 or 4 MeV, and they go up to maybe 7 or 8 MeV. They're produced in fission, and they're entirely nu-E bar. There's basically no contamination of others, assuming no oscillations. If you're close enough, there's no oscillations. You can get enormous fluxes from a reactor. Reactors pump out neutrinos at enormous rates. It's something like 2 times 10 to the 20 per second for a gigawatt reactor. They have actually been used to search for sevens at current, past, and future reactors. But the reason this is difficult for sevens is that you get very low recoil energies, which makes it very, very difficult to actually see the recoils. And I'll come back to that in a little bit. Oh, in fact, I'll come to it right now. So the points I want to make here is that the cross-section for sevens and the maximum recoil energy both increase approximately as the square of the neutrino energy. And so here's a plot on the left here. This is the maximum recoil energy you get from sevens as a function of neutrino energy. So it goes as E squared over m. This is for a medium-sized nucleus, so argon 40. If you have a few MeV neutrino here, such as what you get from a reactor, the maximum recoil energy is less than 1 keV. And so that is really, really experimentally hard to see. It's not impossible, but it's very challenging. But if you go up to, say, 30 MeV, the maximum recoil energy is over 10 keV, and that extra little oomph actually puts it in reach within for a lot of detector technologies. Furthermore, the cross-section goes as the square, and so the plot on the right here is now a distribution. This is the recoil energy distribution you expect, and here I made it for a monochromatic neutrino, and these two lines are for the same flux of neutrinos. Our reactors actually get more flux, but just for the illustration purpose, I assume the same flux of neutrinos. So if you take 3 MeV neutrinos, typical of a reactor, here you see this is argon also, the maximum recoil energy is less than 1 keV. If you take a 30 MeV neutrino, not only is the recoil energy now greater than 10 keV, but per neutrino flux, you get because the cross-section is higher, you get 2 orders of magnitude more recoils. So you get more with the extra, and you get more oomph in the recoils. Now you might say, why not go to higher energy still? But you can't go crazy because the coherence condition has to be satisfied. If you have too high energy neutrinos, the probability of a high momentum transfer becomes large, and you get a suppressed coherent cross-section. And you really have to stay below about 50 MeV, or you start to scatter off the nucleons inside the nucleus rather than the nucleus itself. And so we have kind of a sweet spot, which is neutrinos of a few tens of MeV. Now it's fortunate that we actually are able to make neutrinos artificially in that energy range. And these are neutrinos from pion decay at rest, or stopped pion neutrinos. And the way you make these is you slam protons into a target. That makes hadrons, and if the protons don't have too high energy, it's mostly pions that you make. And then the pions, if they stop, will decay at rest. From pi plus decaying at rest, you get a new mu, which is a 2-body decay, which gives you a monochromatic neutrino, which is prompt. The decay is a fast one, and that has a precise energy of about 29.9 MeV. Then the muon, which it will decay at rest as well, has a 3-body decay, and so you get a range of neutrino energies on a 2.2 microsecond time scale, which is the decay time of the muon. And this spectrum is well understood from weak physics. And so you get, from pion decaying at rest, you get neutrinos up to about 50 MeV of a well-known flavor and energy composition. Now this kind of source has actually been used before for neutrino physics of various kinds. And so here's a map here showing in blue past neutrino sources that have been used from pion decay at rest that have been used for neutrinos. The green ones are current ones and the red ones are the future ones. And so we have Los Alamos and ISIS in the UK, which have been used in the past. This was the LSND experiment. The current experiments here, current sources here, there's the SNS, which I'll say more about. There's a much weaker decay at rest source from the BNV at Fermilab, and then one in Japan. And then future ones, there's the ESS and the Chinese Spallation neutron source. This doesn't mean this is off the coast of Australia, it just means it doesn't have a site yet. The devil is planned. So here's my figure of merit plot for these different kinds of neutrino sources. So this axis here is the power of the protons on the source, which is roughly proportional to the neutrino flux that you get. This axis here is the background rejection factor. This is 1 over the duty cycle, which is, duty cycle is the fraction of time the beam is on. And what you want is for this to be large. You want all the pulses to come in very short time periods, separated by at least a few pion decay lifetimes. And so you want to be out here in the upper right of this plot. And I've plotted these different sources on this plot here. And what you see is that the SNS here is out at a really quite good position there. So let me tell you a little bit more about the spallation neutron source, or neutrino source, as we like to call it. This is at Oak Ridge National Laboratory. It's in Tennessee. The proton beam energy is about a GeV. The total power actually now is routinely up to 1.4 megawatts. This is really not designed for neutrinos. It's really for producing neutrons for material science and all other kinds of stuff. It has a short timescale beam. It's about a few hundred nanoseconds proton beam width at 60 hertz. It's got this terrifying liquid mercury target. It's an enormous thing. And this is so huge and dense that pretty much every pion that is produced in it will immediately come to a halt and decay at rest, so that is actually very good for neutrino physics. And the really good thing about this is that the neutrinos are free. And it's actually all just very good luck. This thing was not built for neutrino physics at all, but it turns out that it's absolutely wonderful. I just have to make the point here that these are not this kind of free neutrinos. It's actually highest quality. You couldn't really design a better source for neutrinos for decay at rest. It's really great. Here's what the time structure of the source looks like. So this is nanoseconds here, and so this is arbitrary units, just what it looks like. Actually, it's not arbitrary units, it's unit full. These are the neutrinos that come from pion decay in time with the proton pulse. So those are 30 MeV neutrinos in red here. These blue ones are the anti-nu-mu's and the nu-e's that come on a 2.2 microsecond muon decay timescale. And this comes at 60 hertz, which gives you a background rejection factor of about a few times 10 to the minus 4, which is very nice. That's equivalent to being actually some distance underground in terms of background rejection. And another point is that it's very clean. It's also kind of a sweet spot in proton energy. If you make your proton energies too high, you start to make a lot of junk in the beam. You make kaons, you have pions that decay in flight, and you get kinds of junk at the high energy end of your spectrum. So this is the same, this is arbitrary units. This is the same spectrum from pion decay at rest that I showed you before on a log scale. And this is the kind of contamination that you get from the SNS source, which is there, but it's down by many orders of magnitude. So it's actually, compared to other sources, for example, JParc, it's actually super clean and really, really very little uncertainty from that kind of extra high energy stuff. Okay, so that's the source. I hope I've convinced you the SNS is fabulous. So now let me talk about detection. I mentioned it a little bit before. It's just like the little tiny thump you get from a WIMP, and we really benefit from a lot of technology from the last several decades. And there are different ways of coupling energy into something that you can see. So there's many strategies, and they're all used for low energy event detection, for dark matter and other things. You can measure phonons, or heat, and that's a strategy. You can drift ionization and collect it. So here you feel a little pulse, warm pulse, here you feel a zap. You can also collect photons, and some of the energy will couple into light, and there's different strategies for doing that. In dark matter world, you can actually use more than one of these strategies at the same time and actually use the ratio of energy going into different channels to help discriminate signal from background. In fact, we haven't done that yet, but it's something that we could do in the future for sevens. Okay, so here's the Coherent Collaboration. It's about 80 members from 20 institutions and 4 countries. Has existed since 2014. And here are the detector technologies that we're using at the SNS to go after sevens. And so we've got a cesium iodide crystal, which was developed at University of Chicago, where the channel that we use for observing the energy is scintillation light. So you see little flashes of light there when sevens events occurs. It's a 14.5 kilogram crystal. I think that's a picture of the prototype. It's 20 meters from the source. I'll show you a map in a bit. We also have deployed now liquid argon and sodium iodide scintillating crystal. And I'll say a little bit more about all of these in the future. And germanium is not yet deployed. So here's where we are. This was also very good luck. We found at the SNS a hallway that we now call Neutrino Alley that goes parallel to the proton beam. So this is where the protons come in. This is where that scary Mercury target is. And there's beam lines actually on the upper level for neutron, using the neutrons in various ways. We just sit there. The neutrinos come out isotropically, so we just sit in the glow of the neutrinos in this hallway here. And it turns out that all this region here is all filled with concrete. And that shields us against neutrons, which actually is really tremendous good luck. We spent actually 2 years or so measuring the neutrons along this hallway until we found that in actually different places, but we found very, very quiet neutron backgrounds in the hallway. And this is where we have the detectors deployed. Germanium is not deployed yet. Cesium iodide is actually at the closest distance, about 19.5 meters away from the source. We have sodium iodide, partly deployed there, and liquid argon in the corner there. So this is what we expect. This is kind of a sanitized recoil energy spectrum. This is not incorporating any efficiencies or backgrounds. This is energy per keV of recoil. This is the recoil energy here, so this is 100 keV. Here you can see the kinematics in action. You get, the lighter the target, the fewer interactions you get, but the more of them get kicked to high energy. And so here, just looking here at the red, is the cesium iodide target. That's one of the heavier ones. That is the heaviest target. The maximum recoil energy here is about 40 keV of recoil energy. Heavier one here, germanium here, so fewer of them, but you get higher energy recoils. Argon here, this is 22 kilograms, higher energy recoils yet. And then we have sodium iodide here. The sodium here, this is the iodine portion of it, actually probably you can't see, but the sodium actually, it's very light and we can actually get energies over 100 keV of recoil energy. And this darker blue here is actually a larger argon, which we're planning for the future. Backgrounds are a thing. I remember when I was in graduate school, I was assigned a project to work on backgrounds, and I thought, oh, that's so boring. But then I realized that it's all about backgrounds. That's what you do in experimental physics. There are usual suspects, cosmic rays. There's ambient and intrinsic radioactivity, and every detector has its own insane features that you have to deal with. Neutrons are especially potentially a problem. All of these are steady state backgrounds, and if you have a pulsed beam, you can characterize the background off beam pulse and then subtract it. And so that you can know exactly what that background is, and it's the square root of that background that disturbs you, not the background itself. However, if you have something that's in time with a beam, which potentially could be neutrons, that is much scarier, and you have to work hard to make sure that you're characterizing those neutron in-time backgrounds. It is a neutron source after all. So we have actually put a lot of effort into that. We also have one kind of interesting background, which is also a signal. Let's maybe call it a friendly fire background. And this is something that we call neutrino-induced neutrons, or NINs. And this is neutrons that you get from neutrinos that interact with a shielding material like lead, such that it will pop out a neutron, and then the neutron can go into the detector and make a little recoil and bake a neutrino event. And that will also be in time with the beam. And so this is something that you have to have a handle on. This can happen in both charge and neutral current way. And it's actually an interesting process in itself because it's something that you can actually use for supernova detection. There's actually a detector at SNOLAB which is, uses this interaction to look for a burst of supernova neutrinos. And so understanding that cross-section is interesting for that as well. And so here's what the cross-section looks like. So this blue one, this is a function of neutrino energy up to 55 MeV. This blue one is the 7's cross-section. The black one is the charge current cross-section, or actually the total of charge and neutral current cross-section on lead. And you can see it's smaller than the 7's cross-section, but it's not that much smaller. So it's something that we have to understand in order to make sure we don't have NIN background in the detector. And it requires a careful shielding design. In fact, the original shielding design was changed in order to make sure you don't want to have your lead right next to your detector, because then you're more vulnerable to NIN backgrounds. You want to have lead on the outside, and then maybe something like polyethylene that will absorb neutrons closer to the inside. Okay, so here's the cesium iodide detector, the detector we have a result from so far. This is a picture in Neutrino Valley. This is the detector being wrapped up with shielding. It's by neutrino standards, it's in fact the world's smallest neutrino detector that has actually seen neutrinos, 14.5 kilograms. That's a graduate student. These are two graduate students who've now graduated. This is Bjorn Schultz from the University of Chicago and Grayson Rich, who is now at Chicago. So here's what it looks like. The detector's in here. There's a layer of poly outside. There's 2 layers of lead. This is a cosmic ray Vito on the outside, and then water shielding on the outside. This is the data taking that led to the first result here. We actually spent 2 years measuring neutron backgrounds. The data taking started for cesium iodide in summer 2015, and by 2 years later, there was a 1.76 times 10 to the 3 protons on target delivered, which is, if you're in the business of long baseline neutrinos, that's a very impressive number. That's a lot of protons on target. Very critical for interpreting the data is what is called a quenching factor, and this is a whole thing. In order to know how much recoil energy you're observing, you need to understand how recoil energy couples into whatever you're measuring, in this case, photons from cesium iodide. And so these are results from 2 separate measurements of the quenching factor done by 2 subgroups of the Coherent Collaboration using a small cesium iodide crystal of the same manufacturer as the one that we used for the measurement. And so it turns out it's about 8% of the energy goes into light that you can see. And the 2 measurements actually disagree somewhat, and we use the disagreement as a systematic uncertainty. And so this is what we know. This is the number that is important for converting observable photoelectrons into actual observed recoil energy. And there's enormous effort put on this kind of thing. Here's the first measurement. This is the first light measurement. This is, these top 2 panels are the measured charge in photoelectrons, which is directly proportional to the recoil energy. And the right-hand plots are for beam on, the left-hand plots are for beam off. The bottom plots are the time distribution for the same data set. And here you can see clearly an excess here. This is for beam on and beam off. There's clearly something there in the beam on. The different colors of the histogram correspond to different flavors of the neutrino beam. And this is in the standard model prediction, which is clearly consistent. The prompt neutron background, which we worried about a lot, is actually very small, and it's all in this first time bin here. And so it's actually a very, very clean measurement. And so this was published in Science about a year ago and made the cover, in fact. So here are the numbers for signal and background and uncertainties. So our total number of signal counts was 134, plus or minus 22. The prediction from the standard model was 173, plus or minus 48, so it's a little bit on the low side. Here are the uncertainties. we estimate about 5% for event selection, with 10% uncertainty on the flux. This is the big uncertainty. This quenching factor is a big deal. That is the biggest thing limiting this measurement right now, and it's actually something that can be improved. For the form factor, it's small, and we have a total 28% uncertainty on the prediction. Here's on a chi-squared plot. This is where the best fit is. This is primarily statistical error. This is a fit using the energy and the time distribution. It's 134. And here's the prediction is, and we reject statistically no sevens at 6.7 sigma, and we're consistent with the standard model at 1 sigma. Now you can interpret this in terms of standard model parameters. Here's a plot here with different measurements of the weak mixing angle, and unfortunately it looks kind of sad. Our uncertainty with a 28% measurement, the error bars even go right off the plot. So that is something we'll improve. However, even that measurement is able to make meaningful constraints on the standard model, which actually is kind of astonishing. So here's the same parameter space plot that I showed you before, and this gray area is the previous constraint, which is from the Charn experiment, which is a few decades ago, neutrino scattering, high energy neutrino scattering experiment. And what we can do, even with our single measurement, and this is a very simple analysis, we can constrain to 90% these epsilons to be within that band, and this is something that we will improve quite a bit in the future. And there's actually, theorists have made other interpretations in the literature, and in fact this is that so-called dark solution that can mess up the mass hierarchy measurement and is already being meaningfully constrained even with this very, very first simple measurement. And I want to point out here that this is the first measurement of low energy neutral current neutrino hadron interaction that actually has a Q dependence. It's the only one so far that has event by event spectral information. There are a couple of neutrino measurements in the past at low energies with nuclei, but they don't have spectral information. They're all just counting measurements. There's one carbon excitation measurement, and there's also a deuterium breakup measurement, but none of those actually have a Q dependence. And so that's, in fact, there's very little other measurements, charge current measurements in this range either. And you can actually use this. This is another theory interpretation. If you assume there's a light mediator, you expect a distortion of the recoil spectrum, and this is another interpretation in terms of parameters in a model that could, in principle, explain the G-2 anomaly. And so here in this space, in fact, those parameters are actually excluded even from this first simple measurement. So that's really very encouraging. And furthermore, although I said that really you need to get better than percent level measurements to start constraining nuclear physics. In fact, we can interpret that still, our measurement in terms of a neutron radius. And this is another recent paper that uses the recoil spectrum to make an actual measurement with uncertainties. It's got an 18% uncertainty of the neutron radius of the nucleus, of the cesium iodide. So this is actually, this is also encouraging. Okay, so what is next? So here again is the n-squared plot. We have one measurement so far, and what we would like to do is map out the n-squared dependence using our detectors. So here are the current and near future deployments in Neutrino Valley. So we have actually 2 detectors now deployed which are measuring sevens. One is the cesium iodide detector, which is still taking data. There's also a liquid argon detector, 22 kilograms. I'll say a little bit more about that in a second. We have a sodium iodide. It's currently not sensitive to sevens. The threshold is too high, but it's measuring charge current currently. We have a neutron background. We have to keep monitoring our neutron background, so we have a neutron detector here. And these are actually detectors dedicated to looking for neutrino-induced neutrons to get a hold of that background and also to measure it in itself for supernova physics. So it's kind of a bit of a motley crew there in the basement. We have now a lot more data in the can. This plot goes until very recently here. You can see this, so the red line is the cesium iodide. We have almost twice the data now of cesium iodide from the first result. And we have now, I guess the argon here is the this one, since 10, it's that yellow one there. We actually have quite a significant amount of argon data as well, which is under analysis. So the farther future here, so this is the status where we are now. Cesium iodide still taking data. Germanium yet to be deployed, will be next year. Liquid argon here was upgraded last year, been taking data for some time. Sodium iodide in high threshold. We are expecting here in the next year or so to deploy new germanium detectors, expansion to a ton scale. Actually, this will probably be more than 1 year. We're putting in a proposal this year for that. We do have 2.5 tons of sodium iodide in hand, and we'll be expanding that in the short term, and actually may get up to 9 tons, and also find some, we may be purchasing some high purity sodium iodide as well. So let me zoom in a little bit more on some of these detectors. This is the single phase liquid argon, which has been running for a while. It's very simple detector. It's just a bucket of liquid argon used by photon multiplier tubes for the to measure the scintillation. It was recently upgraded with better reflection and wavelength shifting on the PMTs and the inner part of the detector. This is a detector actually that was borrowed from Fermilab. And the future of that, we're putting in a proposal now for a ton scale liquid argon detector, which can actually use a lot of the same infrastructure for that. And this is actually also interesting for looking at charge current interactions. I'm actually personally interested in this, since this is the interaction that's important for supernova neutrinos and dune. So we should be able to make a reasonable cross-section measurement, inclusive cross-section measurement of the charge current interaction. High purity germanium. This has the benefit of actually potentially less than 1 keV recoil sensitivity. The quenching factor is relatively well measured and can do reasonable timing. And so the plan for this is to use, we were originally going to use some old Majorana detectors, but it looks now like a better path is to deploy new high purity low background detectors. And then sodium iodide, we have actually up to 9 tons of leftover detectors from an old US Homeland Security program in this bar form. We have to refurbish them in order to allow a high gain and therefore a low threshold for 7s. But we are now deploying 185 kilograms to go after the charge current interaction, which was measured once before, but not at a very precise level. And for future deployments, the reason also, you want to measure that n-squared dependence, but it's actually very valuable to have multiple targets because you can constrain beyond the standard model physics that way. This is just an example of a sensitivity study for NSI. This again is that same example parameter space. And the blue here is the, you can see it peeking out there, is the current measurement. And if you have multiple targets, you can actually narrow it down to these 2 lines. You can actually cancel uncertainties by having different targets, and which have different, the standard model has different N and Z dependence. And so that's another motivation for having multiple measurements. And then for systematic uncertainties, this is the table I showed you before. The dominant uncertainty is this quenching factor, and we are actually, we're doing reanalysis of some of the previous measurements, and this is actually a very important thing. It's kind of a pedestrian thing, but it's very important for understanding, for reducing the systematics for the measurements. One other thing I want to mention is this flux uncertainty is a 10% uncertainty, and it is common to all of the detectors. The quenching factor uncertainty is something that's different for every detector, but this is common to all the detectors, and it is something that we will eventually limit us, and we want to reduce it. And what we have a plan for now, we're putting a proposal in, is for a heavy water detector. The idea is that you want to, if you don't know the flux, the cross-section must be well known, and there's very little information on cross-sections in that energy range. The only things that are well known are elastic scattering on electrons, but that is a tiny cross-section, so you need a huge detector, so that's very hard. Also, inverse beta decay, UV bar and protons is well known, but that is impossible for us because we don't have any UV bars. The only other thing is the cross-section on, the charge current cross-section on deuterium, which is known to about 2%. And so the idea here is to use heavy water in order to measure the spectrum of electrons from charge current interactions in deuterium, and that should give us a few percent precision on flux normalization with a 1.3-ton detector deployed in Neutrino Valley. So this is one of our main activities now. Okay, so I think I will stop there. So here's my summary. The main physics ideas here is that 7s is a large cross-section. It's got tiny recoils, which makes it hard. It goes as n squared. It's now accessible with new low energy threshold detectors. And the thing that has really made this happen is getting a little bit of extra oomph from having the pion decay at rest neutrinos that are a little bit higher energy. We've made the first measurement with Coherent, with the cesium iodide detector, the SNS. This is, this very first measurement has put meaningful bounds on beyond the standard model physics. It's really just the beginning. We have lots of ideas underway. We have multiple targets, ideas for upgrades. We actually have other ideas beyond what I showed you. You have to be careful to not get distracted. There's too many possible things to do. I can mention also that there's other 7s experiments that are going forward at reactors. In fact, we heard at Neutrino 2018, there's indications of 2 sigma statistical measurement at a reactor. These are much more difficult, but there's also developments in detector technology which may help these end up joining the fun. So I will stop there.
Okay, so thanks a lot, Kate, for this very nice and complete talk. Is there any question? Okay.
Thank you very much, Kate. One question on mapping out this n-squared dependence and whether the breaking of the coherent approximation is a concern. Because I thought you said, I mean, the stop ion source is very nice, but it's kind of a high energy tail, and you above 50 MeV, you said it may break for for light targets. So I wonder if how would that manifest if you break? You see the cross-section that does not go as n-squared, it's depleted, and then you don't know if
So the breaking should be well understood. It's basically described by the form factor. And so, in fact, the breaking of coherence is incorporated in this difference. So this black line is for a point-light target, and the green line is for a non-point-light target, basically demonstrating it's not fully coherent. But the dependence is still well understood. The uncertainty in that form factor is a very small width of that line.
I see, okay. So it's in there and you said it.
Yeah.
Thank you.
Yeah, so.
Any other question?
When you measure the recoil neutrinos, do you know, I mean, that you have a ground state and also an excited state of the nucleus?
So there are, I mean, there's incoherent interactions and inelastic interactions that will give you excitations of the final state nucleus. But those, in fact, we will eventually have to worry about those, but they are down by quite a large factor. So a factor of 10, yeah. So in fact, we haven't included those as background in our first measurement. When we get to this argon detector, in fact, that's what that peak is. That's inelastic.
That's because your form factor there, these energies, I mean, is very close to 1. I mean,
right.
So your form factor
is
produces only about a factor of 1/2 maximum.
Yeah.
So, okay, then you're lucky.
Yeah.
Good.
Yeah. But in fact, those are interesting to measure as well. So we would like to measure those in a big enough detector. But they should be also experimentally distinguishable in principle, because the recoils, actually, for instance, in argon, it depends on the detector. In argon, actually cesium iodide, it's hard to distinguish, I think. But in argon, we use pulse shape discrimination to distinguish recoils from gamma and electron-like events. And so events like this from neutral current inelastic excitations will look like gamma rays and will look very different from the recoils.
Can you tell us a little bit about the advantages and drawbacks of using nuclear reactor neutrinos? I've heard about the ricochet thing.
Yeah, so in fact, I think we even have a table. I wonder if it's probably hidden. Let's see. Yeah, okay, so here's my pro and con table. So basically, reactor neutrinos, the advantage is huge amounts of neutrinos. However, it's only one flavor, which is fine, except that if you have flavor-sensitive physics, you won't necessarily be sensitive to it if it's only for muon neutrinos or something. The drawbacks are, first of all, the lower cross-section, which is compensated by higher flux at some level. And basically, you need thresholds of your detector less than 1 keV. So usually, you need for germanium, for example, 1 or 200, maybe 200 EV or so threshold, which is just very challenging. There are actually a bunch of detectors which are, maybe I didn't have a table for a different talk. Let's see. Backup slides. Oh, here it is. Yes, okay. So these are existing experiments that are going after reactor neutrinos, and so they're really trying to push down the threshold very low. And that's not just whether the detector can see the energy, but backgrounds are terrible. And so, for example, there are these bolometer detectors, which are very interesting, but they're currently only very tiny masses, gram scale kind of things. But if that could be scaled up, that would be fantastic. Germanium is probably the near-term thing. There's the CONUS experiment, which is that kind of thing, which should be sensitive. Ricochet is germanium, and I think zinc is the other thing. You could, in principle, do with noble liquids, but that's harder to get the threshold down. There's also a thing called CONI, which uses CCDs. And so, there's a lot of different kinds of technology trying to address it. But it's really, the hard thing is getting the threshold down, and the backgrounds are also hard because the reactor is usually, it's on or off for long periods of time. You don't have a good duty cycle.
Okay, I would like to know what is exactly the limiting, what is limiting the precision or the uncertainty in the quenching measurement of the quenching factor for the CCMI iodide, for example.
So those are very difficult experiments. So the way it's measured is with you use neutrons, and so you fire neutrons of a known energy, and then you measure the recoil. You measure the energy deposition for a particular recoil angle, and those experiments are just very difficult to do. I mean, it's not statistically limited, but the systematics are large. I mean, in fact, I guess you could see on the plot here. I mean, there's also, it seems like there's unknown systematics there, because these are two different measurements, and those are the estimated error bars, including systematics, and they don't agree. And so that's what we did is we just said, okay, let's assume it's flat, and we'll take the difference to be the systematic. And so it's not even really understood what that difference is due to. And actually, this data is under reanalysis now, so we may be able to do better. But it's, these are just tricky experiments.
Another question?
I was wondering, so the use of other sensitive detector materials like lanthanum bromide or so is ruled out because of the self-activity of the use of other sensitive detector materials like lanthanum bromide, lanthanum chloride, and so on. This is ruled out for these experiments because of the self-activity, or is there any
never heard
particular
of
explanation?
I've never heard of using lanthanum bromide. I don't know. I mean, it's true you need a low radioactive background material, or you will be swamped. But I actually don't know specifically about lanthanum bromide or whether it's been considered or not.
Any last question? Okay.
Yes, I like there's one question. When you show the form factor, the graph form factor, I remember that there appeared J1. J1 instead of J0.
Oh.
You just mentioned that your data could be used to learn details on the form factor.
This one?
Yes, that one, right? It appears J1 instead of J0. I was expecting to.
This is the Bessel function. Helm. This is the Helm form factor, yeah. And it's this is a Bessel function.
Yes, but I was expecting to see the J naught instead of J1.
This is just for P-wave couplings. When you have, for example, neutron or a pion, then this factor appears there because you have a P-wave coupling. But in the coherent, it's right, J0.
Okay, I think I cut and paste this from the paper.
Well, no, it's giving you the Q dependent. It's telling you that
it is divided by
It is divided by QR.
Divided by QR.
Divided by QR. I mean, this is a sine over
Yeah, causality, but
minus cos or something. Yeah, some
but
form
it
like
is
that.
slow.
but it will give you from this.
But then,
I have a.
the next order, you have the exponential and the Bessel function. You just fix with the parameter in the exponential.
And one J1 and not J0.
Yeah, I use not can put a in the J1.
So we've actually looked at different. I wonder if I can find another one. This is an internal. I don't know if I have this here. We've actually looked at a bunch of different functional forms, and they actually are very similar. This is a. What happens when we're just talking about this internally recently? Let's see what it is. So these are the forms. So this is the one. This is the Helm one. That's what it looks like if you write out the Bessel function. This is another one that this is the one we used for our prediction in the paper, and this is we also got a numerical one from a theorist, from Chuck Horowitz, and they all look very similar. So you get very, very similar answers. So, we estimate the form factor uncertainty on the prediction due to the form factor choice as 5%, which is probably a bit generous. You can also try varying the neutron radius, and that gives you 5%-ish uncertainty. Neutron spin gives different issues, so it's pretty well understood, or well, who knows, according to the theory that we're using.
So your form factor is a Fourier transform of the spatial size of the neutron.
Yeah.
And we said something about the transition from coherent to incoherent, from quantum to classical physics, I guess. Is that a first with your experiment, or are there other experiments that...
I don't know if that's a first. I don't know. Yeah, good question.
Because other form factors they're all Fourier transforms, I guess, of space, but they need not be the transition from coherent to incoherent.
Yeah, I guess that's true.
I mean, it depends whether you have, for example, when you emit a pion, it's a scalar, and so you expect the spin flip, I guess. I don't know. Okay. But actually, there was a paper recently on the archive that I haven't worked through yet that discussed the issue of what does it actually mean to be coherent, and 40 years ago, I remember asking Norman Cole what was known about the quantum to classical transition. And when he was alive, he said, he got a gleam in his eye, and he said, that's the $1 million question. I think it's still a valid question. Maybe you have a first, I don't know. Maybe people here know whether.
I don't know, yeah.
Okay, so if there is no other questions, let's thank Kate again.